In all of our aromatic substitution reactions so far, we've always been looking at electrophilic aromatic substitution reactions, where we're using the electron density of our ring to attack some electrophile, and then we end up kicking off our hydrogen here, acting as that electrophile that gets substituted for in our reaction. Now, of course, as we know from our earlier studies of organic chemistry, we can also do substitution reactions with nucleophiles. So we can do our typical SN1 or SN2 mechanism, and this allows us to replace one nucleophile for another. So what if we try to do an aromatic substitution reaction with a nucleophile, or a nucleophilic aromatic substitution reaction? Well, of course, in this case, we can't use our hydrogen anymore as our leaving group breaking off because it's not a nucleophile. So we're going to have to modify our aromatic compound here and add on some kind of leaving group that will act as our nucleophile that's getting substituted in this reaction. So now we have this additional nucleophilic leaving group, and we can break that off to complete a nucleophilic aromatic substitution reaction. So what happens when we bring in a strong nucleophile, such as our methoxide shown here, to react with our aromatic compound that contains that nucleophilic leaving group? Well, a strong nucleophile, of course, wants to give electron density over to our aromatic ring, specifically right here at our more electrophilic carbon, due to that nucleophilic leaving group that's attached. Right? Of course, as always, we have our dipole here, where that electronegative bromine is kind of pulling electron density away, creating this more electrophilic carbon there adjacent to it. Now, of course, this is very counter to what we've previously seen with our electrophilic aromatic substitution reactions, where it's always our ring using that double bond to attack something that's electrophilic. Right? So a ring really, we think of it as wanting to attack. In this case, we're going to need it to get attacked by our nucleophile. So for our nucleophilic aromatic substitution reactions, we need to add something that's going to help to pull extra electron density out of our ring and make it easier to receive those extra electrons from our nucleophile. So this means we're going to need electron withdrawing groups, which of course we talked about in our previous lecture. All right, so if we add on something like our nitrate here, that's going to be pulling electron density away from our ring and then facilitating the attack of that nucleophile onto our aromatic compound. So we're seeing two key requirements here for this nucleophilic aromatic substitution reaction. We need a nucleophilic leaving group, such as a halogen, and we need electron withdrawing groups to help to pull electron density out of our ring and make it easier for that nucleophile to attack. Now let's look at the mechanism here. So as we've said before, right, we can't do SN2 reactions with sp2 hybridized carbons. This is partly because of the hybridization and the structure of that. And of course the other problem here is that if we're going to attack here and kick off our bromine at the same time, this attack always has to be a backside attack in a normal SN2 mechanism. And in this case, the backside of our bromine is actually right in the middle of our ring. Right? So we can't attack and break off at the same time as suggested here. So we're going to need a slightly different mechanism for our nucleophilic aromatic substitution reaction. This mechanism is actually going to look fairly similar to our electrophilic aromatic substitution reaction. So our first step here is going to be the addition of our nucleophile. So we're going to attack with that electron-rich nucleophile. And again, we can't kick off our leaving group immediately. So instead, we're going to move our double bond out of the way. So we can move this up here. That makes room for a new bond to form to our nucleophile. And of course, it's going to create a carbanion, in this case, on that carbon of our aromatic compound. So we have our electron withdrawing group. We have now a negative charge sitting here with the lone pair. We've got our other double bonds in the ring. And we have both our nucleophilic leaving group and our new nucleophile sitting here attached to the same carbon. So you'll notice here that as we attack with our nucleophile, we've broken our aromaticity here, right? We no longer have each of our carbons sp2 hybridized with that resonance and conjugation between all of our carbons. So this is, again, very similar to that electrophilic substitution reaction where we lose our aromaticity in the first step, right? The only difference here is that instead of forming that arenium carbocation, we instead have this carbanion here with our negative charge in our formerly aromatic ring system. So this is again going to be our rate limiting step because we're forming an unstable intermediate where we've lost that aromatic stabilization of our ring structure. So our second step then is going to be to restore aromaticity, right? We want to get back that resonance energy stabilization, and we do this by eliminating our nucleophilic leaving group. So again, it's going to look very similar to that electrophilic aromatic substitution reaction, except in this case we have our extra electrons inside of our ring. We use up that anion, we break off our leaving group here of our halogen, and we end up with our final product. And of course in our final product now we have that new nucleophile that we substituted on, our methoxide nucleophile, and we have all three of our double bonds within the ring are back as we restore the aromaticity. And of course our bromine ion over here will break off as their leaving group to create our anionic bromide ion. So final products here. Again, of course, we took one nucleophile, substituted it onto our ring, and released that other nucleophile as our nucleophilic leaving group. Again, the steps are very similar, right? The first step, we're forming some unstable ion where we lose our aromaticity. Second step, we break off a leaving group and restore that aromaticity. The only difference here really between that nucleophilic versus electrophilic reaction is where our electrons are moving, right? Our electrons are flowing into the ring to form an anion and then flowing out as we kick off our leaving group. Before, of course, they were flowing out and attacking the electrophile, and then we would deprotonate and bring electrons back in to eliminate that rhenium cation and form our products. So it's essentially the same as that electrophilic substitution reaction, just the opposite. Now, of course, as we look at our rate limiting step, so we see our key components of that rate limiting step are the nucleophile and our aromatic compound. So similar to our SN2 reaction, the rate for this reaction is going to be based on both the concentrations of our nucleophile and our aromatic compound. So the rate is going to be K times the nucleophile concentration times the concentration of our aromatic compound. I'm representing any general nucleophile as Nu. My X is representing our halogen-based leaving group here. So as we walk through that mechanism, of course you should have seen the importance of that first step where we form that unstable anionic intermediate where we've lost our resonance. Now, of course, this first step relies on our electron withdrawing group, as I said before, where that's helping to pull electron density away and accelerate the attack of these extra electrons from our nucleophile into our aromatic ring. Now, of course, with electrophilic aromatic substitution reactions, we also saw that the position of our withdrawing group or our donating group would affect our reaction as well. So let's look at how that position affects our nucleophilic aromatic substitution reactions as well here. So in the reaction that I've shown here, we have our bromine here as our reactive site, and our electron withdrawing group is on the adjacent carbon. So this would be an ortho position for our substituent, right, since it's adjacent to that reactive site. For our nucleophilic substitution reactions, the reactive site is always going to be where we have the halogen, which is acting as our nucleophilic leaving group. So currently we're at the ortho position, we attack, we move that double bond, we form our anion, and notice that anion is sitting right next to this electron withdrawing group. Right? So our nitrogen is trying to pull electrons toward itself so it can stabilize that positive charge. We can actually show this using resonance structures. Right? So we can actually pull that lone pair out, make a double bond here, push these electrons out to the oxygen to make room for that new double bond. And if we draw out this resonance structure, so we've moved and created a new double bond here to our nitrogen. We now have single bonds to each of our oxygens, and our oxygens are both negatively charged. So in this resonance structure, we've eliminated the negative charge in our carbon, and we've now pushed it out onto our oxygen instead. Of course, oxygens are more electronegative, so they're more used to carrying that negative charge, and we've then been able to stabilize that negative charge through this resonance. So it's actually a good thing to have that negative charge next to our electron withdrawing group. It can actually pull it out and stabilize it through these resonance structures. So if our electron withdrawing group is ortho, then it will speed up our reaction. Let's compare this to an alternate scenario where our electron withdrawing group is meta with respect to our reactive site with our nucleophilic leaving group. So again, our first step looks exactly the same. We attack right next to our leaving group, and we have to move our double bond out of the way to make room for that new bond. We're going to create a carbanion. We have our bromine added on here. Got our new nucleophile. We have our negative charge in our lone pair, double bonds, and of course our electron withdrawing group. Notice how our negative charge now is not next to our nitrate group, our electron withdrawing group, and we can't show this extra resonance here to our nitro group itself. So we can try to move this over. So let's try to jump over here. Now, as we move those electrons, this double bond is also going to have to move to make room. So this will move over here, and we create a new anion. So our new structure looks like this. We've successfully moved our negative charge. But our negative charge is still not adjacent to that electron withdrawing group where we'd be able to get that extra stabilization with our nitrogen and that resonance there. Right? So we can still move this negative charge around the ring in both of these cases, as we're used to seeing for our electrophilic aromatic substitution reactions. But the difference between our ortho and our meta is that in our meta substitution pattern, we're never able to get that negative charge next to that electron withdrawing group. Right? As I draw my third structure here, of course, now I have that negative charge at the bottom of the ring, and it's even further away from my electron withdrawing nitro group. So in none of my resonance structures here am I able to get that negative charge next to my electron withdrawing group, where I'd be able to have that extra stabilization with that electron withdrawing group. So my meta reaction here is slower because we can't stabilize our unstable intermediate. And if we actually drew out the para reaction, we find that both our ortho and para reactions are faster because they both have intermediates here where that negative charge can get stabilized by our electron withdrawing groups. So it's kind of a similar conclusion to what we saw for our electrophilic aromatic substitution, right? Where we can get sped up when we have certain groups that are ortho or para with respect to our reactive site. the difference here is that now electron withdrawing groups are speeding us up, and electron donating groups would actually slow down this reaction, right? So it's the reverse, again, from that electrophilic aromatic substitution reaction, right? Withdrawing speeds up nucleophile reactions, donating speeds up electrophile reactions. So we really want to be careful about our terminology. You can't just refer to a nitro group as a deactivating group. It deactivates electrophilic aromatic substitution reactions, but it activates our nucleophilic aromatic substitution reactions. The last factor that we need to consider here for our nucleophilic aromatic substitution reaction is our leaving group itself. Now previously with SN2 and SN1 reactions, we saw that larger leaving groups like bromine or iodine reacted very quickly because they had weaker bonds, and so they were able to break off more easily, right? So they accelerated the formation of the intermediate, which then accelerated the formation of product. Now if you look at our reactant here and our unstable intermediate in our rate limiting step, you'll notice that our leaving group is still attached. So we won't see that normal trend of leaving group ability that we've seen before, because breaking off of a leaving group doesn't affect our rate limiting step, right? That happens in the second step, which is much faster and doesn't affect the rate of our reaction very significantly. So in this case, we need to consider something else. Now remember, our leaving group, of course, is pulling electron density towards itself. That's what creates kind of our little partial positive charge that then gets attacked by our nucleophile. So we want something that's going to be pulling more electron density towards itself so that we create a larger partial positive charge and encourage the attack of our nucleophile. Right? Essentially, we want our leaving group to be an electron withdrawing group itself. Now, the strength of that electron withdrawing effect, of course, is dependent on the electronegativity of our leaving group. So the key here is going to be how electronegative our leaving group is, which of course, as we know, electronegativity increases as we go towards the top right-hand side of our periodic table, with fluorine as our most electronegative halogen, then chlorine, and then bromine, and then iodine. So our reaction rate will actually be fastest with fluorine and slowest with iodine, in the exact reverse of the trend that we saw for SN2 and SN1 reactions. There, iodine again reacted faster because it had the larger and weaker bond, whereas here, our bond isn't breaking the rate limiting step, and it's just based on which is the most electronegative. So again, these two different key factors will control all of our nucleophilic substitution reactions. The leaving group itself, as well as what electron withdrawing substituents we have on the ring that can help to pull electrons away and facilitate this reaction. Overall, what we're able to do here is substitute halogens for other compounds on our ring. Right? So we can easily add halogens as we've seen before with our halogenation reaction of our electrophilic aromatic substitution mechanism. And then of course with this nucleophilic aromatic substitution reaction, we can take those halogens and replace them with more complicated nucleophiles to create a wide variety of different aromatic compounds.